Today, we will use a scientific perspective to explore the complex truth behind emergencies. Following the New Year's Day ANA collision in Japan, two extremely serious and extremely rare accidents in the history of human aviation have occurred in various places in the past 2 days. The latest incident was a Scandinavian Airbus A320neo passenger plane with registration number SEROE. On January 6th, it was photographed having a serious hard landing at Ronaldo Airport in Madeira, Portugal. The aircraft was descending. The speed was so fast that the fuselage of the aircraft fell heavily to the ground, and there was even flames coming from the left side. Subsequently, the plane went around after being bounced and hovered in the air for more than 20 minutes, before diverting to the nearby Gran Canaria airport. A hard landing event of this magnitude would have a major impact on the damage to the aircraft body and the safety of passengers. It has also been said to be very rare in aviation history. The place where this incident occurred is Cristiano Ronaldo Airport, one of the most dangerous airports in the world, also known as Santa Catarina Airport. It is located in Funchal, Madeira Island, Portugal. The second incident occurred at 9:06 a.m. on January 6th. According to the latest news on the BBC website, Alaska Airlines Flight AS-1282 took off from Portland, Oregon, and was destined for Ontario, California. There were 171 passengers and 6 crew members on board. Alaska Airlines Boeing 737 MAX 9 cabin has 16 first-class seats, 24 premium economy class seats, and 138 regular economy class seats. This flight was almost full. The 737 MAX 9 is the second model in the Boeing 737 MAX family to be put into operation. It is an elongated fuselage product of the basic MAX 8. The all-economy class layout can accommodate 220 seats, and the standard 2-class layout provided by Boeing can also accommodate 193 seats, which is a dozen more seats than the MAX 8. Alaska Airlines MAX 9 has a relatively small number of seats, which paved the way for today's rare incident. Shockingly, 6 minutes after takeoff, the aircraft, registration number N704AL, which had been delivered just over 2 months ago, climbed to almost 5,000 meters. At this time, there was a loud noise from the rear left side of the plane, and screams came from the cabin. Passengers shouted loudly. Because of the cabin wall, a big hole actually appeared. Everyone realized that at this moment, they would most likely fly out of the plane and disappear into the sky 10,000 meters high. Thank you for liking, leaving comments, subscribing, and turning on the little bell. We will update every day. At that time, the air in the fuselage roared and poured out from the breech, and the seat covers near the breech were torn off by the airflow and flew outside. Fortunately, on such a full plane, the seat next to me was empty. Fortunately, it was during the takeoff and climb phase, and most of the passengers were wearing seat belts. The crew quickly executed the fuselage depressurization emergency procedures, and the plane returned to Portland Airport more than 20 minutes later. The passengers and crew were all safe and sound. Thousands of meters of failure, I'm still in shock. What's the reason behind it? An emergency exit door on the rear left side of the fuselage flew off when the fuselage was pressurized. And that location in the fuselage is not the emergency exit seat. The reason is the low-density cabin layout chosen by Alaska Airlines. The number of exits on an aircraft is determined by the number of seats in the aircraft. In order to meet the 90-second emergency evacuation standards of various certification bodies in the aviation industry, the more seats there are in the aircraft, the more exits there will be. It is not easy to add a normal passenger cabin. If you need to add seats, the emergency exit is usually added. MAX 9 has one more pair of emergency exit hatches behind the wings than MAX 8. This is a Class 2 emergency exit, measuring no less than 20 by 44 inches. In the larger 737 MAX 10 model, which is currently undergoing certification, this location is a larger Class 1 emergency exit. However, Alaska Airlines has a low-density layout with few passengers at full capacity. According to regulations, these two emergency doors are not required. However, this demand is not worth Boeing's specially customized MAX 9 fuselage. So according to Boeing, the two cabin doors were permanently locked and the interior was covered with ordinary cabin wall panels. However, I never expected that the covering panels that should focus on safety would be so childish and fly off at any time. On a new aircraft, the emergency door that was permanently locked by Boeing collapsed during flight. It was a unique accident in the entire history of aviation. The history of Boeing's MAX passenger aircraft is full of misfortunes. On March 10, 2019, an Ethiopian Airlines Boeing 737 MAX 8 crashed during takeoff. In October 2018, Indonesian Lion Air Flight 610 crashed. The aircraft involved in both accidents were 737 MAX 8s that were less than half a year old. Both crashes occurred during takeoff, and both were suspected to be due to a faulty angle of attack sensor, or the overreaction of the maneuvering characteristics enhancement system led to a vicious confrontation between the pilot and the computer navigation, which eventually caused the aircraft to stall and crash, causing many civil aviation authorities and airlines to worry about the safety of the passenger aircraft. During 2019, all 374 Boeing 737 MAX series passenger aircraft delivered were grounded. It was not until November 18, 2020, that some national aviation authorities began to restore flight permissions for the 737 MAX series passenger aircraft. Therefore, this incident has cast a new dark cloud on Boeing, which has frequently reported assembly quality problems, especially its MAX assembly line. After this incident, Alaska Airlines has grounded all 65 of its Boeing 737 MAX 9 aircraft, pending further inspections. Currently, the FAA has ordered the temporary grounding of Boeing 737 MAX 9 aircraft. In fact, looking at the history of global aviation safety, the situation has been greatly improved compared to before. Statistics show that the accident rate of commercial airliners has dropped significantly over the past 30 years. Calculated as an accident rate per million flying hours, the accident rate per million flying hours was 0.83 during 1985 to 2000, while it dropped to 0.32 during 2001 to 2015. Aircraft manufacturers are also constantly improving designs to make commercial airliners safer and more reliable. However, in the daily operation of general passenger flights, various accidents still occur frequently. First, the bird strike incident. This is one of the most common and frequent accidents involving commercial airliners. When an aircraft encounters a large flock of birds, it is easy to cause the birds to be sucked into the engine or the birds to penetrate the wings, engine fan blades, etc. This will pose certain risks to flight safety. However, in most bird strike accidents, crews can land safely. Followed by the runway landing accident. This includes landing overshoot, runway excursion, hard landing, etc. The causes of these accidents may be improper operation by pilots, bad weather, or aircraft system failures. In this type of accident, serious ones will cause damage to the aircraft, while minor ones will only cause punctures in the aircraft's tires and minor scratches on the fuselage. What cannot be ignored are military attacks on shipping routes. There have been several incidents of being shot down in the air in history. Such incidents usually cause heavy casualties, but the probability is extremely low. As military tensions have cooled in recent years, such incidents have become rare. Even more important are accidents caused by extreme weather. If you encounter extreme cyclones, blizzards, etc., it may seriously affect the flight and even cause a crash. In this type of incident, the crew can reduce the risk by appropriately choosing an alternate airport or raising the altitude to avoid the incident. What deserves attention is the breakup and disintegration in the air. There have been several incidents in history where aircraft broke apart and crashed due to mid-air explosions or structural failures. Such events are often extremely devastating and have a low chance of survival. Such incidents could be caused by a terrorist attack or by aircraft structural defects or metal fatigue. What cannot be ignored is the failure of the onboard system. For example, loss of cabin pressure and failure of important systems such as engines, avionics, and flight control systems will pose serious threats to flight safety. This requires the crew to respond quickly and formulate an emergency plan. Some minor system failures can result in safe landings at alternate airports. When general passenger aircraft perform route tasks, they usually have a series of plans and standard handling procedures to deal with various emergencies and failures. First of all, when facing a loss of pressure in the cockpit/cabin, the crew will quickly activate the system and quickly descend to an altitude below 10,000 feet, while notifying control and issuing the 7700 emergency code. Select an appropriate nearby airport to make an alternate landing based on the situation. If the situation cannot be controlled, the crew should consider ejecting at low altitude over the offshore sea as soon as possible. Secondly, when encountering severe weather, such as blizzards, hurricanes, etc., the crew will observe weather trends in advance, make significant detours to avoid severe weather areas, or choose an opportunity to land at an alternative airport. If necessary, activate the vertical height in the air to avoid strong convection areas. If you have entered extreme weather, you should maintain a low speed and stable flight posture and attitude to prevent aerodynamic overshoot or spin. More importantly, engine fires are more serious situations. At this time, the crew will immediately shut down the corresponding engine and maintain flight by increasing the thrust of the relative engine. Calculate the single-engine command parameters and maximum flight time according to the single-engine flight manual, and select the nearest airworthy airport for alternate landing as soon as possible. Perform a supergravity landing if necessary. It is worth noting that when fuel leaks, the unit will immediately shut down the corresponding fuel pumps and valves and cut off the fuel supply. Try to choose a suitable airport for emergency landing based on the remaining fuel before the fuel runs out. Additional roll distance may need to be considered when landing. What cannot be ignored is that if the landing gear cannot be lowered, the crew will try to relieve the obstruction through the emergency gear release program. If it cannot be resolved, the situation is explained to air traffic control and eventually a belly pulley landing is performed on the runway. This requires flexible operation to reduce speed and reduce damage to the body. At the same time, when the flight control system such as oil pressure, power supply, and operating system fails, The crew will activate the backup system for control. Some faults may require additional handling according to the troubleshooting guidelines in the flight manual, adjustment of command parameters, or the need to divert as soon as possible. In fact, during the landing process of the aircraft, if the contact between the wheels and the runway is too violent, it cannot decelerate normally and causes a certain degree of damage to the fuselage or landing gear. This is the so-called hard landing, which is generally caused by a series of reasons. First of all, if the crew's judgment and operation are improper during the approach and landing, a hard landing will occur. For example, a misjudgment overestimates the actual wind speed, causing the landing speed to be too fast and unable to slow down in time. Or the aircraft was not fully trimmed, causing a large longitudinal overload to passengers. This type of landing error is the main cause of hard landings. Secondly, weather conditions will also affect it, especially strong crosswinds and heavy rain. This affects the pilot's vision and speed judgment. Strong winds may cause the aircraft to touch the ground with shock or be overturned by sudden wind shear. It's also easy to land too quickly. This type of damage is usually concentrated on the landing gear. Additionally, runway conditions are relevant. If the track is very slippery due to accumulation of water or ice, the tire grip effect will be greatly reduced, and the braking power will be insufficient to decelerate. Sometimes there may be obstacles such as elk or birds on the runway, and the pilot may temporarily pull back and make violent maneuvers, which may also cause overload damage. What cannot be ignored is that special conditions will also increase the chance of landing accidents. If the lower limit of the maximum landing weight in single-engine mode is reduced, it is easy to cause the landing gear to be overloaded. Or if the flight control system has minor malfunctions and instability before landing, it will also affect the normal landing. This can easily make the landing too heavy and too hard. More importantly, when a hard landing accident occurs, the crew will immediately declare the situation and shut down the engine and fuel to prevent a fire alarm. All onboard mobile equipment also cease generating sparks. Relevant departments will conduct a detailed inspection of the aircraft and landing gear to assess the extent of the damage. For minor ones, the truss can be repaired and continue to serve. For serious ones, it will require long-term repairs or be directly removed from the company and scrapped. On the other hand, usually, the structural design of the aircraft is rigorously calculated and can withstand large loads on the ground and during flight. However, in a few cases, due to fatigue or corrosion of metal materials, some key components may be damaged and fall off under high-altitude stress, resulting in holes in the fuselage. First of all, the cause of such events may be long-term flight missions and frequent changes in altitude, which bring repeated pressure changes to the aircraft body. This will fatigue and weaken key components, such as fuselage outer panels, hatches, porthole frames, and other structures. The metal will develop cracks and tiny folds, or even burst and break. If the fracture part is in an area with greater stress, a chain reaction will occur and a large area will disintegrate. Secondly, if maintenance and repairs are improper and minor fatigue and corrosion damage is not found in the structure, accidents may occur in the long run. In particular, some minor surface damage is difficult to detect, but over time, it will gradually expand into serious hidden dangers. In addition, specific cases of common disintegration at high altitudes include the entire cockpit glass window falling off due to installation errors and fatigue of the metal frame. The cargo door failed and exploded. The underwing skin material fell off due to glue failure. These may cause the fuselage to lose pressure instantly and pose a serious threat to the structural integrity. More importantly, once the fuselage breaks, the crew must make a judgment and take action as soon as possible. They first tried to descend quickly to reduce the aerodynamic impact, while at the same time decelerating and reducing overload through maneuvers. Then select the nearest suitable airport for emergency landing. If the damage is too great to control, they can also choose to eject at low altitude over the offshore sea to escape. In general, although the overall safety of commercial aircraft has been greatly improved, there are still certain hidden dangers and technical needs in some areas that need to be further improved. First, better predictions of airborne turbulence and wind shear are needed. This type of aerodynamic phenomenon is very complex and changeable, and there are still certain scientific blind spots on its mechanism. Aircraft often encounter unforeseen strong turbulence, and the judgment and response to extreme situations still need to be improved. There is still much room for improvement in related meteorological research and detection equipment. Secondly, there is also an urgent need for improvement in anti-icing and de-icing systems. In particular, new types of mixed-phase precipitation that are prone to freezing pose a problem for anti-icing and de-icing. Efficient drainage and de-icing equipment is required around the clock. There are also technical bottlenecks in de-icing some major parts such as the engine air inlet. At the same time, material fatigue and structural life control are also eternal issues. This determines the safe service life of the aircraft. Better non-destructive testing methods need to be developed to monitor the true status of aircraft structures and materials in real time. Material substitution in some key parts also has a long way to go. What cannot be ignored is that although modern passenger aircraft can land safely in the extreme case of two engine failures, there is theoretically room for improvement in the technical reserves of single-engine and parking flights, including better utilization of remaining engine performance. This is also related to the ultimate challenge of the aircraft's minimum control speed. At present, airlines have also improved the training standards of crew members. Through simulator training, pilots can face more analog experiences of extreme weather conditions and aircraft failures. This can effectively reduce flight accidents. At the same time, airlines are also using more advanced flight software and automation systems, such as advanced automatic flight systems, better navigation instruments, and more accurate weather radars. These modern equipment greatly reduce the probability of accidents caused by human error. On the other hand, air traffic control continues to improve. Using satellite positioning and data link technology, air traffic control can instantly see more aircraft location information, improving command efficiency. In addition, the Air Traffic Control Department promotes advanced flight navigation programs such as RNAV, so that aircraft can fly more accurately and reduce the risk of close encounters. In the future, with the rapid development of humans and machines, air traffic control departments will also face new challenges and need to establish a more powerful air traffic management system to manage the complex airspace environment. Thank you for liking, leaving a message, subscribing and turning on the little bell. We will update the latest news from around the world every day. Continue to use a scientific perspective to explore the complex truth behind meteorological events.